Now that we understand reflection and refraction of wavefront, let us now move on to diffraction. Diffraction at IGCSE level is very easy. You do not have much things to learn about in diffraction. It is very simply introduced at IGCSE level. So let us start with diffraction. So what is diffraction? So when wave pass an edge or an obstacle, they spread out or they diffract. So let us see what is happening. So you have a set of incident wavefronts. Let us mark the incident wavefronts. These are your incident wavefronts where I am putting the tick. They come and they are crossing through a barrier. The green thing that you see here, it is a barrier, and therefore if it is a barrier, it will have an ending point, which is the edge, the corner of the barrier. So what do you see? When the wavefront are passing from a barrier, the wavefront on the other side are also present behind the barrier. So the wavefront does not look something like this. The wavefronts do not look as a straight line like this. No. Rather, they are extending behind the barrier as well. If you see, they are extending, they are present behind the barrier as well. They are present behind the obstacle as well. This is called diffraction. So when the waves, they travel, they pass an edge or a boundary, or whenever they pass through a gap, they spread out. They are spreading out. This is your spreading out zone. They spread out. This is called diffraction. So I hope it should be clear from the picture, which is very clear. The presence of the wave behind the obstacle, behind the boundary, is why? It is because of diffraction. So two simple properties of diffraction. Property number 1. Please take out your pens, your paper, your notebook, and please copy this. Very common. Narrower is the gap, more the waves spread out. So if you compare the two pictures, smaller is the gap or narrow is the gap, more is the spreading out pattern that you see. More the spreading out pattern that you see here. The second point is the same thing, the other way around. The wider is the gap, the less the waves spread out. Same thing said in the other way, right? So that's property number 1. The diffraction depends on the width of the gap, but please do remember one important point to consider where the students might lose mark. The spacing between the wavefronts before and after diffraction, they are precisely the same. They are same. Same wavelength. The wavelength does not change during the diffraction process. The gap between the wavefronts will stay the same. The gap between the wavefronts, the spacing between the wavefronts should stay the same. This is an important concept that you need to remember for your exam. In your exam, the question might give you some incident wavefronts. You have to draw the diffracted wavefront. How do you draw the diffracted wavefronts? Taking care that the spacing between the wavefronts should not change. The spacing before and the spacing after the diffraction should stay the same. Otherwise, you lose marks. Very important thing. Alright, so let's move on. Another diffraction property. Larger is the wavelength, more the waves diffract. Smaller the wavelength, lesser the waves diffract. Please note it in your notebooks. Take out your pens, your notebooks, note it down. Look at the picture. The width gap, the width size is the same in both the pictures, but the wavelength is different. How do you see that the wavelength is different? Check it for yourself. Compare the spacing between the wavefronts. Compare the spacing. This is your wavelength 1. Let's say this is your wavelength 2. Spacing, clearly you see that the wavelength 2 is greater than wavelength 1. Which wave is diffracting more? Diffraction is happening more for the wave which has a greater wavelength. Longer the wavelength, more is the diffraction. Larger the wavelength, more the waves diffract. Here also if you see that the wavelength should remain the same. If it was lambda 2 before diffraction, after diffraction also it should remain the same. If it was lambda 1 in the first picture before diffraction, it should say lambda 1 after the diffraction as well. The wavelength is not changing in both the pictures before and after the diffraction. Be careful about these facts in your answer, that the diffraction does not and will never change. It will never change the wavelength. Even the reflection does not change the wavelength. It is just the refraction which changes the wavelength, which we'll understand just now. Now sound bends around obstacles such as walls and building, which is why we can hear sound around the corner. Light wave, when it passes through tiny holes and slits, they suggest that light waves have much shorter wavelength than sound. So let us compare sound and light. You are given sound and light. Sound has a very high wavelength. Light has very tiny or very small wavelength. Light and sound. So which will diffract more? It will diffract. Sound will diffract more. Light will diffract less. Let us understand these 2 points. Suppose that there is a TV on in one other room. Even if the door is closed, you can still the TV sound. Why? Because the sound diffracts more. It can diffract through the small holes in the door, small cracks in the doors, or it can even diffract around an open door. So even if the TV is on in one of the rooms, it can be heard in other rooms as well, because the sound waves can turn around and reach you. Why? Because they have a high wavelength, so they bend about or diffract more. So therefore it is audible in every room. But can you see the TV from another room? Say that you are in your study room and the TV is not in your clear straight line of sight. It is somewhere located. Can you see the TV from your study room which is kept in the living room? No, you cannot. You can hear, but you cannot see. Why? Because light has smaller wavelength and it diffracts less. Sound can be heard or it can spread around everywhere, but light cannot be seen or it cannot spread about everywhere. Therefore, seeing things which are not in the same straight line is impossible. If you want to see a thing, you have to be in the same straight line, because the light does not bend so much or it does not diffract so much. It diffracts less because it has a smaller wavelength. Similarly, the radio signals, the signals which are caught by the radio devices, they can bend around so much because they have a long wavelength. They can bend around hills, buildings, and therefore the radio signals can be caught anywhere and you can listen to your music. Alright, very important point. So let us now understand all the three parameters which are there present in the wave equation. We know that V is equal to F lambda. This is your wave equation. When we talk about reflection, neither the frequency nor the wavelength and hence the speed also does not change. The frequency, wavelength and the speed for reflection, none of them change. Similarly for diffraction, the frequency, wavelength and the speed, none of these 3 factors change. But for refraction, the speed and the wavelength, they do change, but the frequency does not change. If you look at the frequency, it does not change for reflection, refraction or diffraction. Right? So for the refraction we have just done today. For the refraction, whenever the speed will go up, the wavelength will go up. If the speed goes down, the wavelength goes down. They exist in this pattern. Alright, this was all about your waves. The next chapter will be on light. But before we proceed to the next chapter, the next topic will solve some IGCSE exam style questions on waves.